Ladies and gentlemen, welcome to the 19th group exhibit Hydrogen and Fuel Cells. We invite you to take a seat and listen to the exciting presentation, enjoy beverages that are on the house. We are going to be talking about hydrogen storage without the high pressure, and our next speaker is Kevin Brundish, the Chief Operating Officer of Cella Energy Ltd.
Morning.
Good morning.
Morning.
So, Kevin, for those who do not know Cella Energy yet, can you please give us first a brief introduction of the company?
Sure, yeah. So Cella Energy is set up in 2011. It's a spin-out from a national lab in the UK called the Rutherford Appleton Laboratory. And that's where all the invention of the technology came from, in combination with Oxford University and the University College of London. So we've been set up to commercialise the hydrogen storage technology that was developed there, which is a solid format hydrogen storage technology.
Can everybody hear him all right?
You hear me okay? Yeah. Excellent. So I've got an example of the material here, and it's a plastic-like pellet solution that contains around about 10% by weight of hydrogen. And to get the hydrogen out, you heat it up to about 100 degrees centigrade. So that's the basis of the company.
Okay, so tell us, what can you do with this? What are the applications? What do you do? What do you use it for?
Well, it's a hydrogen storage technology, so it has a wide range of opportunities in applications. In the near term, what we've been looking at is applying this technology on a battery style system, so low power, sort of hundreds of watts up to kilowatts level, and looking at getting a very long duration system. So we're looking to apply that into markets such as defence, for a long duration power system, for UAVs and soldier portable equipment. But longer term, that same system could be used in laptops or portable consumer electronics. So we're looking to do that this current year, and we'll have systems up and running this year on that power scale. But in the longer term, we also feel this is a good solution for an automotive fuel.
So you want to use it as alternative to high pressure hydrogen? That's
exactly the point. So this material here doesn't need any high pressure. You can store it in a standard plastic canister. And the only additional energy you need is 100 degrees C to raise it up to that temperature so that it releases hydrogen. And there's a hydrogen source available as long as you have the material there. But no high pressure required and no cryogenic temperatures. So all of that side of is disappeared on having this material.
Is it a new idea?
Chemical hydrides have been around for a little while, so there's big programs in the US that have looked at chemical hydrides being a solution for automotive fuels and other power systems. But the challenge behind the normal chemical hydrides is that they release their energy very slowly, and they actually do melt before they yield their hydrogen. So we've created a polymer of a plastic and a chemical hydride, which overcomes all of those challenges and makes it a practical system. So we can now use that in a flowing system, because these pellets can be flown as if they were a liquid. So again, considering the longer term automotive application, we're looking at really using something that the user is familiar with, a flowing fuel that is stored in standard tanks and can be pumped around and quite quickly.
You said longer term automotive applications. How long term are we talking?
Well, we've developed this material and it's ready. So right now what we're doing in the automotive side is working with two UK automotive partners to put the system in place that will be in the vehicle. So that's going to be ready in about 12 months. So we'll be looking to work that up thereafter and introduce it into the market sometime 12 to 18 months from today.
Okay, from what I know, new technologies are always very expensive. Are you expensive?
Well, this isn't produced in very high volumes right now, so the price points need to come down from today. But we're working with a large US and Germany-based chemical engineering company, and we've done some forecasting where we can get the cost base of the material to. One of the points about the material is it can be recycled. So after use, it can be taken back to the chemical plant and recycled. And once that process is fully up and running at volume, we're looking at gasoline-style costs for this material.
Wow, that's impressive. But how exactly does it work? So automotive application sounds very interesting to me. So you have a car, you have a fuel cell in there, you have a refueling tank. How does this system work together with the solid material?
Okay, so flowing the material is one of the first things to know about, and that's simply done by blowing it with a gas medium, so air in this case. It would use a standard automotive tank as it stays right now. It will be moved into a heater area where it will be sealed off and the hydrogen will be released upon heating. And then once it's released its hydrogen, the material will be returned to the tank where it can be stored until it's refueled. New pellets containing hydrogen will be put back into the vehicle, and the hydrogen, the pellets that have the spent hydrogen will be taken away back to the reprocessing plant. Actually, it's easier to describe that when we've got a display on the stand that if you come and have a look at, we can describe that process a little easier.
What's your booth number?
Oh, E69, so it's just down that corridor.
Okay, and where does the hydrogen come from that you are using? Where do you?
So there's two processes where the hydrogen would come from. In the first instance, the first fill, so making the pellets from new, would use hydrogen, and we're looking at this being a large-scale process. So we'd be using, we're looking to co-locate that on a refinery field and using some of the waste hydrogen, but otherwise we can use natural gas in the same chemical process. Once we get to the recycling process, it uses ammonia as the source of hydrogen, and again, it's a chemical process, so it's chemically engineered, and the hydrogen is chemically bound in the solid.
So if you look at the car, then it must be environmentally clean. But if you take the well-to-wheel process, the entire process, how is it? Is it very green or
it is
moderately green?
Well, we've done that study. So we've done a well-to-wheel study using an approach called the GREET analysis, which people may be familiar with. It's a process of looking at well-to-wheel analysis, replacing 5% of the automotive fuel. And it's a process that was developed by Argonne National Labs. And when we run through that process, we get a CO2 solution which is equal, if not better, to high-pressure hydrogen. In all cases with hydrogen, you have to have some energy, and it really depends on how green that energy is in creating the hydrogen. This approach lends itself to having some renewable energy supplies, and therefore gives a very low carbon footprint. But it really depends on the source of that energy.
Okay, and a bit different question. If you use, so from what I understand, you use this technology to compete with battery technology?
Sure, yes. So in a slightly different format, if we just place discrete amounts of this material onto a heater pad in an array, we can individually heat up the material and yield hydrogen, which could then run through a fuel cell. So we can scale this down to a sort of battery scale, watts to kilowatts level. And then we're looking at competing with things like lithium ion. We're looking to get 3 to 5 times the energy density or the specific energy that lithium ion can achieve. So we see that as one of the first applications in the near term in defence markets and then potentially into consumer electronics.
Okay, thank you. And what about the safety issues? Can I take it? Can I touch it? Can I eat it?
Yeah, it's an inert material essentially, and the polymer creates an encapsulation of the hydride, so it gets safe in that sense. But moreover, there's no gaseous hydrogen until you actually heat it and release it. So it's a safe material in that sense. There's no gas build-up until you actually heat it and release the hydrogen.
And in the car, where does the heat come from? How do you heat it in the car?
Well, we would need to start up. So if it was in an automotive application, we would need an electrical heater to start it off. But we can then start using some of the waste heat from the... I mean, this hydrogen, once released, can run either in an IC engine or more likely a fuel cell. And both of those produce heat, which can be fed back into the release process. So that was where we get the heat from in the system, fully integrated.
Oh, that's easy. And to transport this, do you need any special conditions? Like, do you need to cool it down or?
No, it's safe across a wide variety of temperatures. It can be transported in the road tankers that we see today, transporting oil-based. And because there's no vapor, we would need less stringent challenges in transporting it compared to things like gas.
Is it explosive?
It will burn, but it's not explosive. So if you actually set fire to it, as will plastics in general and hydrogen-bearing materials, it would burn. But because there's no vapor, it doesn't have that explosive risk.
Okay, and in the cell phones, did I get you right that basically the weight can be even smaller than the battery and the size can be smaller than the battery?
Yes, if you wanted the same energy as a lithium-ion battery, it will be a smaller, lighter weight system. We're looking to get 3 to 5 times more energy per kilogram in the system.
For the same price as the battery?
Indeed, yes. So we've got to get the volume of the material sales up to get that scale. So that we are currently working with some chemical engineering companies to scale the material production, which will drive the price down.
Okay. Does anybody have any questions? Please introduce yourself briefly.
Hello, my name is Thomas Wald here, and I wanted to know how's the exact name of the polymer you're using to save the hydrogen?
We actually use a couple of polymers, but we're currently using a polymer PEO. PEO, yeah. I couldn't give you any more information than that because I'm not a detailed chemist, but we have a chemist on our stand, so if you want to know some more, please come down. I think it's got maybe a follow-up. And
when you use it in a fuel cell, what kind of a fuel cell is the best? Is there?
It's a PEM fuel cell approach, yeah, because it's just using hydrogen.
For all the polymers to produce, you need oil. It's only 4% from the whole usage of the world of the oil, but there are some percent you have to use. So isn't it a little bit less green if you do it with polymers?
Well, in the well-to-wheel analysis, we've counted for all of the different components that get drawn into the end product. So you get the overall CO2 side of it. And actually the polymer use is very small in this particular compound. It's really there just to provide some of the structural integrity, but also does a couple of other functions when we're releasing the energy or when we're releasing the hydrogen.
Do you know how much pressure you need to get the hydrogen into the polymers?
It's a chemical reaction, so this isn't about pushing the hydrogen in.
No pressure at all?
No, it's temperature driven rather than pressure driven.
Oh, nice.
Yeah.
Thanks.
Yeah.
Thank you. Any other questions?
Zakiul Kubir, Clear Edge Power. Just one quick question. Is there any cyclic durability issue? How many cycles can you do?
Because it's a chemical recycling process rather than a sort of refilling, we're actually breaking it down and then reforming it. So it's actually more of a yield and an efficiency of that chemical manufacturing process, not so much you know carrying on using it. So it can be done repeatedly in that sense.
We have another question.
You mentioned the temperature at which these things start to release hydrogen. For me, it's interesting. If I happen to have a black painted car that sits in the sun, you could imagine a situation where slowly the hydrogen gets released, or at least the temperature at which it is released is reached. Yeah. So what happens in that case?
We've done extensive shelf life tests looking at automotive style certification temperatures, and the release is negligible if at all. So it really doesn't release until you get above the activation temperature. When it starts to release, it's then an exothermic reaction which self-sustains. So as far as the shelf life goes and storage, we don't see a challenge there.
No more questions. Well, I have one a bit provocative question for you. So if you want to use this in the cars, you need to sort of convince the entire industry, you need to convince the car manufacturers, you need to convince the infrastructure providers. How do you want to do that?
Well, part of doing that is our attendance here and me speaking here, because we want to raise the profile of what we've been doing, and the stand we have here is doing just that. So really we are now talking to a range of different automotive partners to look at how we would demonstrate the technology, and then we'll move on from there.
And you will convince the entire industry?
I'm sorry?
And you will be able to convince the entire industry?
Because we have we don't see the need for the same infrastructure costs to put in some of the other solutions, so we believe there's a compelling argument that can convince the industry.
Well, I'm convinced. Thank you very much.
Thank you.